Hello everyone, here we'll be talking about section 3.11, which is a topic on hyperbolic functions. And you kind of see here that the definitions of these functions, well, they have names that are very similar to trig functions. And in fact, well, they're named because they have a lot of properties that are similar to that of trig functions. And they involve applications that go obviously beyond what we'll be seeing, but they creep up every now and then in different applications of mathematics, so it's important that we give them names, and these are the names. So there's hyperbolic sine, hyperbolic cosine, hyperbolic tangent, hyperbolic cosecant, hyperbolic secant, and hyperbolic cotangent. Now, the definitions for sine and cosine hyperbolic are these: e to the x plus negative x, well I guess this is e to the x minus e to the negative x over 2. And for hyperbolic cosine, it's e to the x plus e to the negative x all over 2. Tangent is defined to be hyperbolic sine over hyperbolic cosine. Cosecant is the reciprocal of the hyperbolic sine. Hyperbolic secant is the reciprocal of hyperbolic cosine. And hyperbolic cotangent obviously is the reciprocal of hyperbolic tangent. Now obviously, it's a lot to say the name. So for that reason, there are these kind of short phrases people say usually. They're not traditional by any means, like they're not standard, I guess. But I'm going to use it. It's kind of like short. It's kind of slang, really. So for a hyperbolic sine, it would be cinch, which I know sounds funny. There's no C in between, but that's what it kind of looks like. For a cosine hyperbolic or a hyperbolic cosine, it would be cosh and maybe tanch. I don't know. You can go from there maybe and figure out your own way of calling these. But again, all of these other four, besides these two, are built up from this definition of these two. And of course, we see here some hyperbolic identities, and they'll relate very much to their trig counterparts. So you'll notice that cinch here is an odd function, much like sine is an odd function. Meaning if you take cinch of a negative value, it's negative cinch of that value. And cosh here is even, meaning if you take cosh of a negative value, the negative goes away completely. And it's equal to just cosh of that value without the negative, essentially. And then we'll see here which kind of tries to mimic the Pythagorean identity, but falls short of the middle sign here. And we'll talk actually about that right now before moving on to the other ones. So here I'll say Pythagorean identity. It's not quite a Pythagorean identity. In fact, maybe you can call it the fundamental hyperbolic function identity or something like that. But, right. So let's actually dive deep into that right now. So now, if you recall from trig functions, sine and cosine actually satisfy this with a plus. So the trig versions. Cosine squared plus sine squared is equal to 1. So what that means is kind of like we've seen in trigonometry, hopefully you remember, that if you have a unit circle here, notice the equation of the unit circle centered at the origin is x squared plus y squared equals 1. And if you have a given point on the unit circle, x comma y, and the angle from the positive x-axis to that point, straight line radius like that, is theta, then x will be cosine of theta, and then y would be sine of theta. In other words, these trig functions, cosine and sine, follow points on a unit circle, which makes sense that they satisfy this equation here, because that's, well, the equation of the unit circle. So the fact that cosine and sine actually satisfy this Pythagorean identity means that they satisfy this equation, so they represent points on the unit circle. So that makes sense. But now, equivalently, if we looked at this as, well, this is x squared plus y squared equals 1, but this is, let's say, something like x squared minus y squared equals 1, that's not the equation of a circle, that's the equation of a hyperbola. So here, x squared minus y squared equals 1 is the so-called unit hyperbola. So it actually passes through the x and, the x-axis here, negative 1 and 1. Doesn't pass through the y-axis at all. I'm not going to get too much into detail, but basically the hyperbola is constructed from this kind of 1-by-1 box, something like this. And if you create diagonals in this box, you essentially get the asymptotes of the hyperbola. And the height of the box would indeed be 1 and negative 1. So that's why it's called the unit hyperbola, but we don't really need to know that. And in fact, you'll notice here, we have an angle theta that are the arguments of sine and cosine. Here you can say that x and y, again, a point on the hyperbola, unit hyperbola, are represented by cosh and cinch of a parameter t. These are what are known as parametric equations. T usually stands for time. Here, theta is obviously the angle, but what this value t actually represents, believe it or not, is twice this shaded area that I've shaded here. So if you connect from the origin to this point, not the angle is what t represents, but the area of this inner shaded region, twice that area would be t actually. But that's not of particular importance, that's just what it is. So in fact, mainly what we'll be doing in this section is just going based on these definitions of Cinch and Koch, we can find properties, and then actually the next step will be to find derivatives, and then explore certain things kind of similar to what we've seen for trig identities. Okay, good. Now the last identities here I mentioned are the sum identities for Cinch and Koch, and they're very similar to that of their trig counterparts, sine and cosine. So it's a good idea if you look back at those, but I'll just tell you right now. For sine, it's exactly the same, only without the h's, of course. And I haven't mentioned this yet, but of course the h's stand for hyperbolic, so I think that goes without saying. But anyways, for Koch here, is this the same as its cosine trigonometric counterpart? And it is not. This positive sign should be a negative, actually, if that were the case. And in fact, we'll see right now, for derivatives, well, they're not quite the same, but they're super similar. So we'll see some of those derivatives right now, and then from there, we'll explore more properties. So let's take a look at that right now. All right, so before moving on to the derivatives, actually, I feel we deserve to see a proof of one of those properties. And in fact, which one better than the Pythagorean identity equivalent? So now, of course, to prove this, all we'll be using, and for anything we'll be seeing in this section really, are the definitions of Cinch and Koch. So what we want to do here is we want to square them. So I'm going to square Koch, and I just kind of recall what that is. That's the one that's plus of e to the x and its reciprocal, all divided by 2, minus e to the x minus e to the negative x, all over 2 squared. And we expand these out. Notice they're both going to be over 4. This is minus. So what we expect to get is that the numerators combine to 4 somehow. And notice here, all we really need to do is just, well, square this binomial. It's going to be the sum of the squares with a middle term in the middle, and the middle term will be their product times 2. Notice their product is just 1 because they're reciprocals, and 1 times 2 is 2. So really we're going to get e to the 2x plus 2 plus e to the negative x, like that. And I'll allow you to verify that on your own, but really what I said kind of explains it. And here, well, we're going to get the same exact thing, only instead of positive 2 in the middle, because of the negative sign, their product is negative, so we'll get a negative 2 in the middle. And by the way, these should have been squared, so these are actually e to the 2x, e to the negative 2x. Didn't mean to lie to you, just forgot that. And here, let's see that it's same exact thing. E to the 2x, but instead of a minus in the middle instead of a positive, and then plus e to the negative 2x. Now the funny thing happening here is since we're subtracting this, right, this subtraction, so we're doing this minus that, we can bring the negative in like this, and really what that does is just distributes into each of those and changes their sign. So I'll actually do that like this, if you don't mind, kind of erasing as I go along, which I normally don't like to do, but in this setting it's okay. And we can now combine them over the same one denominator, because they have the common denominator 4. And we expect to get 4 on top after canceling some things, so that we get 1. And that is the case actually, because notice these cancel, and these actually cancel as well. So we're left with this 2 plus 2, which is indeed 1. That canceling didn't actually come out very well on the camera, so let me do that part again. There we go, that probably looks a little better, it's brighter. So again, 2 plus 2 is 1, 2 plus 2 is 4. There we go, and 4 over 4 is 1. That's what I meant. Awesome. So that actually completes the proof, so I'll put a tombstone here completing the proof. And now for derivatives, well, we're in for a treat because I want to show all of these, at least as much as I can. Hope we have time for it. But let's start off with, so I'm going to kind of prove here, but I don't really have too much space to actually do all of them, so I may erase as I go along, we'll see. So first off for sine, notice sine is e to the x minus e to the negative x all over 2. If you don't mind, I'm going to write this as 1/2 times so that we can see this as just being a constant times this function. So when we take its derivative, which I'll just denote by arrow with a d on top, the 1/2 is a constant, so by constant multiple rule it comes out for free. Derivative of e to the x is itself, derivative of e to the negative x is itself times derivative of the power by chain rule. So it's actually e to the negative x times negative 1. Notice the double negative here, so it's actually plus e to the negative x. And actually, if you rewrite this as being over 2, because again, multiplying by 1/2 is just over 2, so maybe we should have left it like that. Well, you'll notice this is actually just the definition of cosh. So we get this is actually cosh of x. By the way, on the previous screen, for some of them I wrote parentheses after the x just to represent Cinch and cosh as functions, just to, I guess, emphasize the fact that they're functions. But very often I'll omit the parentheses, much like I do for sine, cosine, even like ln of x, for instance. But yeah, Cinch and cosh are functions, and the other ones as well. But I'm just omitting the parentheses. So this is cosh of x, so that's good. But now for the derivative of that was Cinch. Now for the derivative of cosh, I want to look at, so maybe I'll leave it like this. So we got e to the x plus e to the negative x over 2. And when we take its derivative, the over 2 part stays because we saw it's just multiplying 1/2. Derivative of e to the x is itself. Derivative of e to the negative x, as we saw, is e to the negative x itself. But by chain rule, a negative 1 comes out because that's a derivative of the power. So really this is minus e to the negative x, which notice is just back to Cinch. And this should be a little striking because, well, what actually it is in the trigonometric counterparts is derivative of cosine is a negative sign. But for hyperbolic, it's just without the negative actually. So sine goes to cosine and cosine goes to sine for hyperbolic functions. Great, so now what about tangent? Oof. Is that going to be that hard to do? I don't think so, because notice, since we have these two and all of these other 4 are based on the definitions of these, we don't actually have to go down to the definition of Cinch and cosh involving the powers of e. So, in fact, let me erase this real quick here, and let's actually just do it right now, live, so to speak, without me cutting to it. So, if we want to take the derivative of tangent, hyperbolic tangent, that is. Let's recall the hyperbolic tangent is hyperbolic sine over hyperbolic cosine, so Cinch over cosh. So really when we take the derivative here, we need to apply the quotient rule. So it's going to be all over the bottom squared. So it's going to be cosh of x, I guess, squared. And by quotient rule, the numerator is derivative of the top, derivative of Cinch is cosh, as we just saw, times regular of the bottom, so cosh times cosh would be cosh squared, just to kind of save space, minus, by quotient rule, regular of the top times derivative of the bottom, so that's regular of the top is Cinch of x, times derivative of the bottom, notice derivative of cosh is Cinch, so Cinch times Cinch is Cinch squared, again, just to save time. And look at this, we have our identity being used. Cosh minus Cinch is 1. So this is just 1 over cosh squared. Which is of course the same as 1 over cosh quantity squared. 1 over cosh is the definition for secant hyperbolic. I don't know how you'd even say that. But that's like shorthand, I don't know how you'd say that, but that's fine. So this is hyperbolic secant squared actually. Which is exactly the kind of equivalence we would get for the trig counterparts. Namely, derivative of tangent is secant squared. All right, so can we do the rest? Maybe I'll just fill them out for you, but maybe not. Maybe let's do it. Let's do it. So let's see. So cosecant hyperbolic. Remember, that's just the reciprocal of sine or Cinch, which I'm going to write like this: Cinch to the negative 1. And again, these arrows represent derivatives, just for shorthand. And now, what I'm going to do actually is I'm going to write 1 over Cinch as Cinch to the negative 1 to use chain rule. Okay? So derivative of x to the negative 1 is negative 1 times x to the negative 2. Much like that. Okay? And the inside stays the same, it's Cinch. But then what? Well, then by chain rule, we multiply by derivative of the inside. Derivative of the inside is cosh. So we can actually write this as cosh over Cinch squared. And it's negative though. Yeah. So it's negative cosh over Cinch squared. And in fact, if you split this up as cosh over cinch, it's going to be negative. So if you split it up as negative cosh over cinch times 1 over cinch, like this. Notice 1 over cinch is cosecant itself, and cosh over cinch is cotangent. So I'll actually write it with cosecant first, though. So this is indeed negative cosecant hyperbolic times hyperbolic cotangent of x. Awesome. And we can do a similar thing for secant. In fact, maybe we can kind of see it here. If that were the case, then it would kind of just be the reciprocal, and you can see that. So again, I kind of don't really like to do this too much, but I'm going to kind of reuse this as a template here and just replace. So if we were to do it for secant hyperbolic or hyperbolic secant, sometimes I say those interchangeably because the h comes after, but that's fine. So notice secant hyperbolic or hyperbolic secant is a reciprocal of cosh. So we can just do this kind of a thing. And then by chain rule, we end up getting this times the derivative of cosh, which is cinch. So then really what we end up getting is exactly this, but with sine on top, or cinch on top, and cosh squared on the bottom. Kind of like you'd expect. So that means you would write this as cinch over cosh times 1 over cosh. I know this sounds kind of funny because of the wording. The wording sounds a little weird. And I hope this isn't too confusing. I know I'm kind of rewording things and going a little all over the place, but it's just for space and time, kind of. So notice cinch over cosh is tangent, 1 over cosh is secant. Oh, this is negative still, though, isn't it? So this is actually negative secant tangent, hyperbolic each. Great. And cotangent, well, we can actually do something similar here, but notice since, well, let me see how we would modify this. So we replace tangent with cotangent. Tangent isn't sine over cosine, but tangent is cosine over sine. So again, using this as kind of a template. Okay. For the quotient rule, it's going to be all over the bottom squared, so it's going to be cinch squared in the bottom. That part's fine. But then notice the quotient rule part on top will say what? It will say derivative of the top times regular of the bottom. That's going to be cinch squared, not cosh squared. Minus regular of the top times derivative of the bottom, and that's going to be cosh squared, not cinch squared. And notice since cosh minus cinch is 1, the other way around in subtraction will be negative 1. So this will be negative 1 over cinch squared. In other words, it's negative cosecant squared. Negative hyperbolic cosecant squared. So I hope that wasn't too much. I mean, obviously, again, I'm going a little over the place. I'm kind of erasing as I go along for some parts. What we end up getting is a really nice result here for these 6 derivatives. It's very similar to what we see from the trig counterparts, but some sign changes, of course. So we're still not done. We're still going to do a bunch more. In fact, right now I want to look at their inverse functions. That's going to be fun. I'm not going to be as thorough as far as going through things, but at least we can see it's all based on the definition of cinch and cosh. Once you have those down, you can write the other things in terms of those and just use those properties in kind of a less detailed way. In other words, you don't have to go to the definition of the powers of E. So I do that for the first ones, but then the rest I just kind of use the names that we've already established, just to make things easier. But you can, if you completely necessary, you can totally do that. Like here, you can totally go down to the definitions of cinch and cosh, and then go from there. But in some cases, you can just use what we already know for cinch and cosh. Anyways, let's move on and see some more properties, and specifically, let's take a look at those inverses right now. Right, so here for inverses, I only want to talk about cinch, cosh, and hyperbolic tangent inverses, but you can construct similar inverses for the other ones for hyperbolic cosecant, secant, and hyperbolic cotangent. Namely, if y is equal to sine inverse or hyperbolic sine inverse of x, then this implies that x is equal to sine hyperbolic or hyperbolic sine, or cinch, however you want to say it, of y. And in fact, this is just definition of inverse, but we're kind of constructing an inverse function based on the definition of inverse and actually seeing if it exists And as it turns out, we haven't even graphed any of these actually. But as it turns out, they only really exist where the functions are one-to-one. And actually, as we saw for sine, cosine, and tangent for those trig functions, we kind of had to make some incisions. I don't know if you remember that or not. But you have to make some cuts of the graphs so that they are one-to-one in certain locations, so that their inverses only exist in certain locations. And that's kind of true here a little bit. And in fact, we'll see in a bit, I'll actually prove the equation for hyperbolic sine inverse. But these are what we end up getting actually. They're actually closed form representations of the inverse functions in terms of ln, which makes a lot of sense. And the reason why it makes a lot of sense is that, well, remember that these are all really expressed as powers of e. And the inverse of e to the x is ln of x. So it's only natural that an expression involving e to the x will have a inverse that's in terms of ln somehow. Now these, by the way, are possible restrictions of x. Notice here this says x is a real number. That means negative infinity to infinity is the domain. So any x actually works. What this tells me actually is that Cinch will be a one-to-one function. Here, for Cauchy inverse, we get something kind of funny. It looks very similar, only instead of x squared plus 1 in the radical, we have x squared minus 1, which could possibly be negative in the radical. Notice x squared plus 1 is always positive, but x squared minus 1 is negative when x is either, well, 1 or bigger, 1 or smaller, I should say. Because if x is smaller than 1 and x squared is smaller than 1, and something smaller than 1 minus 1 is negative, and you can't have a negative inside the radical to get a real number. So for that reason, we say x is bigger than or equal to 1 in this case. Similarly, for this one, we say that x must be in between negative 1 and 1 for the inverse of hyperbolic tangent. And that's because if you actually go out of this region, pick a number that is less than negative 1 or equal to negative 1, in fact, or bigger than or equal to 1, this inside part becomes either negative or 0 or undefined. So notice when you plug in 1, the denominator is 0. When you plug in negative 1, you get 0 over 2, which is 0. But ln of 0 is undefined. 0 is not in the domain of ln. Neither are negative numbers. And in fact, anything outside of that, so bigger than 1 or less than negative 1, will result in this fraction being negative. So that's why we have this restriction here. Anyways, now I'm going to attempt to prove this form, this expression for Cinch inverse. Let's see if we can do it. So recall that, if we're letting y equal Cinch inverse, then from the construction and from really definition of inverse functions, that means if we take Cinch of both sides, we'll get Cinch of y equals Cinch of Cinch inverse of x. Since those are inverses of each other, those will cancel and we'll just get x. So namely, we can undo the Cinch inverse by taking Cinch of the other side. So exactly what this says here. So Cinch of y is just equal to x. But taking Cinch of both sides and then seeing this cancellation here, I think is really the way of doing it. But that's fine. Now, what is Cinch? Well, the definition of Cinch, remember, is e to the y minus e to the negative y all over 2 equals x. We can clear denominators, so I'm going to do that, multiply by 2, might as well. And now, how do we get y by itself? Well, maybe there's a way to, let me see here, maybe there's a way to make one of these 1 somehow. I mean, we could add like a 2 in the middle or something like that. No, that wouldn't work. So there's a little bit of exploring to be done here, but I don't think it's actually too bad. In fact, what I'm going to do is I'm going to pull out the smaller one, which is e to the negative y. So if we do that, pulling out e to the negative y will leave us with e to the 2y minus 1. And that's not super difficult to see because notice we just end up getting, when you distribute back, you add the powers, you just get e to the y for the first one, and then this obviously is going to be e to the negative y for the second term. Okay, but now notice this is really just 1 over e to the y, so we can multiply that to the other side to kind of clear denominators. So we get e to the 2y minus 1 is equal to 2x, e to the y. And we want to get all of the y's on one side, so actually we can subtract this to the right, or subtract this from the right to the left, and add 1 to the right side. So namely, we'll be getting this actually equals 1. So that I hope is not too hard to see. But now we want to pull out e to the y somehow. And this may prove difficult. So let's see, how do we pull out e to the y? Well, I guess what this is kind of reminding me of is a quadratic, because it looks like e to the y squared. So we can write e to the 2y as e to the y squared. And then I guess if we just leave this on this side, so minus 1 equals 0. So this is our kind of, our term. This is like our x, e to the y is kind of like our x in the quadratic. So in fact what I'm going to do actually is I'm going to use quadratic formula, and we'll see what we get. So I'm going to move things around, write this up. We'll use quadratic formula. It won't take too long, and we're almost there actually. Right, so this is what we ended up with, and I wrote it like this so that it reminds us of a quadratic, but in e to the y instead of in a variable x or something like that. So now notice a is 1, b is negative 2x, and c is negative 1. So considering the quadratic formula, we're going to get the variable, quote-unquote variable, e to the y, equal to negative b, which is double negative 2, so positive 2x, double negative 2x, positive 2x, plus or minus the square root of, let's see, it's going to be b squared, so negative 2 quantity squared is going to be 4x squared, minus 4 times a times c, but notice, well, let's just write it like this, 4 times a times c. Yeah, so notice that a is positive 1, c is negative 1. In fact, here we have a double negative. And if you multiply those, you just get positive 4, actually. So that's kind of nice. Notice they both have 4 in common. So in fact, let me kind of do this. If you factor out a 4 here, and then go even further, you can split the radical up. Radical 4 is 2. So you can actually write this as 2 radical x squared plus 1. This is actually coming together kind of nicely. Notice the radical x squared plus 1 part we kind of already see. All over 2a, which is just 2. Now the fact that the numerator both have 2 in common, if you factor that 2 out, like this, then and only then can you cancel these two. So we end up with e to the y is equal to x plus or minus the square root of x squared plus 1. Now as it turns out, the negative is kind of bogus. Because, well, here this says, and this is kind of funny. So this says x could be negative, but if x is negative, well, maybe this is positive to counteract that, like bigger than a negative to counteract that. And that makes sense because x squared plus 1 is always going to be bigger than x. So even if x is negative, that's going to be okay, actually. Maybe I'm thinking too much about it. But really what I want to say is that e to the y is always positive. So I don't think this can ever be negative. Because if it was negative, any x value you plug in would have a smaller minus bigger effect, because since x squared is bigger than x squared plus 1 in the radical is still bigger than x as well. Which looks funny, because if you take away the 1, radical x squared is x, well, it's the absolute value of x. So it's equal to x when x is positive, but since we have that plus 1, it makes it slightly bigger than x. And you can check for yourself. If you make this minus, and you plug in any number of x you like, you'll get a negative value, actually. It'll be small, but it'll still be negative. But since e is a positive number, e to any power, even to a negative power or something like that, will result in a positive number. So for that reason, this must be positive, not negative. Hence the positive here. In fact, the last and final step is to take ln of both sides, and in doing that, we just get y by itself on the left, and then ln of what we've accomplished already on the right, which is x plus the square root of x squared plus 1. And that completes the proof of that equation there. Awesome, totally awesome. You can do something very similar for Cauchy inverse and hyperbolic tangent inverse. You can do it, I'm not going to do it. But now I'm going to maybe mention the derivatives of the inverses, and then we'll try to maybe do some more examples. Right, so even though I didn't mention the inverses of the reciprocals of the hyperbolic functions sine, cosine, and tangent, well, the derivatives are mentioned here. And here are the derivatives of the ones that we did talk about. And in fact, you'll notice that if you compare again to what happened for the inverses of the trig, sine, cosine, tangents, and even cosecant, secant, and cotangent, if you like, there's a lot of similarities. In fact, there's a lot of interesting things going on here. The first thing that kind of catches me is that we have this absolute value of x here, but not here. What's that all about? Why is that the case? Well, I actually think it's the case because, now first note that the domain of sine inverse, hyperbolic sine inverse, is all real x values. Here, the domain of cosine hyperbolic inverse is only when x is bigger than or equal to 1. Okay, so for that reason, maybe we need this because x may be positive, or maybe negative, I should say. But here, x is basically always going to be positive, and the absolute value of that ends up being itself anyways. And in fact, where absolute value comes from, usually in these kinds of things where there was no absolute value before, is from square rooting x squared. And I actually mentioned this earlier. The square root of x squared isn't just x, it's the absolute value of x. Because when x is negative, like imagine negative 2, the square root of negative 2 squared is, negative 2 squared is actually 4, because negative 2 times negative 2 is 4. And the square root of 4 is 2, which is not the original number negative 2, so it kind of helps to write it out, of course. So the square root of negative 2 quantity squared is not equal to negative 2. That's not the case. So the radical and square don't necessarily cancel in that case when x is negative. But if you write absolute value, then this is indeed true. So I think that should kind of help as far as where that comes from, and maybe why it's not the case here due to the domain of inverse cosh. Okay. The next thing that kind of that I find a little striking is look at cotangent and tangent inverse hyperbolic inverses. They appear to be the same, and maybe we'll explore this a little bit. But first, I want to prove to you that the derivative of inverse Cinch is indeed this. There are actually two ways of doing it, because notice we actually have a closed form for a Cinch inverse. But the way I'm going to handle it is the way we would find the derivative for a sine inverse that we actually saw in, I believe we saw this in 3.5 if I'm not mistaken, an implicit differentiation. So if we call it y, then our goal is to find dy dx. But since this is an inverse, we can apply sine hyperbolic to both sides to get this, because that's just definition of the inverse function. Great. Now if we implicitly differentiate, we'll get derivative of this is cosh, but since it's of y, by chain rule it's times dy over dx. And here derivative of x with respect to x is 1. So that means that this is going to be dy dx is equal to 1 over cosh, or secant hyperbolic. But now how can we write this in terms of Cinch? Because Cinch of y is equal to x. And I want to write this back in terms of x somehow. So let's recall this identity. Cosh squared minus x squared, or cosh squared minus Cinch squared, is equal to 1. So that means if we write this with y's, that's certainly true, because it's true for any argument as long as they're both the same. If you solve for cosh of y, you'll have cosh squared is equal to 1 plus Cinch squared, like that. But then, of course, to undo this square, we can just square root both sides. Now notice in doing so, we get a plus or minus. But if you look back at the definition of cosh, it was e to the x plus e to the negative x all over 2. And that's actually always positive because e is a positive number. For Cinch, there's subtraction, so that could result in negatives. But for cosh, it's always positive. So we take the positive radical in this case. And notice that Cinch of y is just x. So that means this becomes 1 over cosh, which is equal to 1 plus Cinch of y squared. But Cinch of y is x, so this is radical 1 plus x squared. And that actually completes the proof for Cinch inverse. And again, you can find it also using the logarithmic form we saw earlier. And you can do all of these other ones just like we did here. And I said I wanted to explore these, so I'm going to erase everything and kind of show that these indeed are the same. Because at first it looks like there may be a mistake. Like, how can two things have the same derivative? we've actually seen a lot of things that have the same derivative. The best example I come up with off the top of my head are constants. So notice 5, 7, 9, those are all different functions. F of x equals 5, f of x equals 9, any number. And their derivatives are all the same, they're all 0. And at first you may think that's kind of a dumb answer, but what that tells you is that if you add a constant to any number or any function, you actually get the same derivative if that constant wasn't there. So maybe that says that tangent hyperbolic is just a constant plus cotangent hyperbolic, or at least for their inverses maybe. That would be kind of hard to show because we'd have to find the logarithmic expression for tangent inverse, which we have, but for cotangent hyperbolic inverse we don't. So instead, let's see if we can maybe use this method to show they're the same. Let's take a look. Right, so here, as I previously mentioned, we're going to compare the derivatives of the inverse of hyperbolic tangent and the inverse of hyperbolic cotangent. The way I'm going about it so far is by using the template we saw for the inverse of Cinch, derivative of that anyways, by first writing it as y, then switching it back to non-inverse, so tangent hyperbolic of y is equal to x. Similarly here, we'll have, I guess you can call it coth maybe, so coth of y is equal to x. Taking derivative implicitly of both sides, we get derivative of tangent, which is secant squared hyperbolic, times dy dx by chain rule. So we kind of see the same things we saw from the previous thing. What we end up with for both of these actually is this. So notice all I'm doing here is multiplying cosine hyperbolic of both sides squared, because since this is really 1 over cosh squared, we can multiply it to the other side. Similarly, since this is negative 1 over sinh squared of y, we can multiply that to both sides. So that's what I get here. And now, again, these are supposedly the same, which sounds a little weird, but notice that these aren't actually the same because y is defined differently for each of them. So it's not just to say that, oh, these are equal. These aren't necessarily equal for all values of y, but when y is inverse of tangent hyperbolic, and when y here is inverse of cotangent hyperbolic, then yeah, maybe they are actually the same expression. So we still have some hope. Again, looking at this, it seems like the hope is lost. But again, considering where y came from, they're not the same y. So for that reason, we do have some hope now. Now, I don't see any other way of doing this without showing you the other versions of the Pythagorean identity, so I'll show you. So remember that we had cosh squared, and I'll write y in this case, minus sinh squared is equal to 1. I wrote it kind of weird. There we go, like this. And now this is, what I'm about to show you is the same way I actually convinced myself that the other ones are true for the trig counterparts. So I'll normally write sine squared plus cosine squared equals 1, and then just divide through by either cosine squared or sine squared to get the other two equivalent Pythagorean identities for trig functions. For hyperbolic, it's the exact same thing. So if we divide everything by sinh, for instance, we get cosh squared over sinh squared. We're dividing through by sinh squared. Cosh over sinh is cotangent. So we get cotangent hyperbolic squared minus, so remember we're dividing by sinh squared, so sinh squared over sinh squared is 1, equals 1 over sinh squared, which is cosecant hyperbolic squared of y. So that's dividing through by sinh squared. Dividing by cosh squared gives us cosh squared over cosh squared, which is 1, minus sinh squared over cosh squared, which is tangent hyperbolic squared, again of y, equals 1 over cosh, which is secant hyperbolic squared. All right, so with that being said, I think we're in an okay spot, but we'll have to write this as a reciprocal of secant. So maybe we should have just done that to begin with. But it wasn't obvious that we'd be using these identities, so that's fine. So let's see, dividing by cosecant hyperbolic squared, perfect. And now using these identities, secant hyperbolic is equal to 1 minus tangent hyperbolic. And notice, tangent hyperbolic of y is just equal to x from this. So this is that squared, so we get 1 over 1 minus x squared. Good. Here, so that completes this proof. But really we're just comparing them to see that they're indeed the same. And I think we're super close. So this is a negative 1 over cosecant hyperbolic squared, which is this. So we get negative 1 over cotangent hyperbolic squared minus 1. And notice cotangent hyperbolic of y is just x. So since this is that squared, this is going to be negative 1 over x squared minus 1. And notice if you bring the negative in the fraction down to the denominator, it just changes the sign, so we can swap the difference there. And then write it as 1 over 1 minus x squared. Awesome. So strange, they end up having the same derivative. It's a little bizarre. Anyways, now, I mean, honestly, I think this would really be the end of the video. I think I've shown enough here. But one thing I haven't shown is evaluations. So there are special values, for example, for sine and cosine for trig. So very often, obviously, we're comparing to the trig counterparts. So notice, for example, sine of pi over 2 is 1, sine of 0 is 0, cosine of pi over 3 is 1/2. And the special values we'll get for these hyperbolics will be something like plugging in, let's say, ln of 2, for instance. Because we plug in ln of 2 into that expression for sinh and cosh, since they're defined by e, then we'll get some nice cancellation and we'll get some special values. So I'm just going to show you some quick evaluations of those before I end the video here. Right, so here we're going to do these evaluations. So I'm writing parentheses here just to, again, emphasize that these are functions. And mainly we're only going to be obviously using the definitions to actually figure out what's going on. So here for sine hyperbolic or sinh, remember that's e to that minus e to the negative that, all over 2. Now here the power is 0 because we're plugging in 0. So notice we're just going to get, well, 1 minus 1 on top, which is 0 over 2, so it's 0 for this first guy. For this one, for cosine hyperbolic, that's e to the inside, ln of 5, plus, instead of minus, e to the negative inside, over 2. Now e to the ln of 5 cancel and just give you 5. But e to the negative ln of 5, not quite the case. We actually need to write it as e to the ln of 5 to the negative 1. Notice this is valid because the power is multiplied to negative ln of 5. And now since e and ln are next to each other, then we can cancel. So this is plus 5 to the negative 1, which by the way is 1 over 5. And this over 2. So in fact, if you just divide top and bottom, not top and bottom, but each of the numerators by 2, we get 5 over 2 plus 1 over 10, which if you want to write this as a common denominator, you can multiply top and bottom, the first one by 5, and you'll get 25 over 10 plus 1 over 10. So this is 26 over 10, which reduces to 13 over 5, funny enough. That is interesting. Tangent hyperbolic of ln of 2. If you want, we can do a similar thing for sine and cosine hyperbolic, and then figure this out. Something I haven't used, though, that I think will be okay for me to use here is the following. And I'll explain why, and it should make a lot of sense to you. So this is e minus e to the negative over the conjugate of this, basically. So e to the ln of 2 plus e to the negative ln of 2. And why is this the case? It's actually pretty obvious to see, even though I didn't really mention it before, but we kind of could have. Tangent hyperbolic is sinh over cosh. So notice if you multiply this by the reciprocal of the definition of cosh, the 2's cancel, so you just get the difference on top over the sum on the bottom. Now we're just going to plug in ln of 2 in place of x. So again, when we see cancellation here, for no negative is in front of ln, we just get 2. But for the one with negatives in front of ln, we get the reciprocal of 2. In fact, notice you can actually bring the negative sign in as a power of 2 using an ln property like we've seen kind of before. So really you get the reciprocal of 2, which again is 1/2. And then here a kind of trick you can do is you can multiply top and bottom by 2. So we'll get 4 minus 1 over 4 plus 1. And this is actually just 3 over 5. So that was kind of fun to see that. Let's see, so secant, again, is 1 over cosh. It's the reciprocal of cosh, so let's just write it like this. E to the 0 plus e to the negative 0. That I think works. In fact, what this kind of tells us is that cosecant hyperbolic of 0 is undefined because we get 1 minus 1 on the bottom. But here for secant, you get 1 plus 1 on the bottom, which is actually 2. So that's 2 over 2 is just 1 for this one. That's kind of funny. Now here, let's see what we get. Remember, this is the reciprocal of Cinch. Cinch is the difference of the x's over 2. So the reciprocal of that will be 2 over the difference. And we're plugging in ln of this. So let me write more space, keep more space here. So we got e to the ln of 1 plus radical 2 minus e to the ln of, e to the negative ln of 1 plus radical 2, like that. Awesome. All right, so these cancel, so we get 1 plus radical 2 on the bottom for the first term, and this is 2 all over that. Okay, good, just making sure we're good. And now we have minus the reciprocal of this, because when there's a negative in front of ln, remember you can bring it as a power, so you get this, which looks really weird. So it's 1 over 1 plus radical 2, just want to be a little more clear about that. But notice what we can do is kind of what we did here, multiply top and bottom by 2 for the third example. So let me show you in red. If we multiply top and bottom by what's giving us this fraction in a fraction situation, is the denominator here, which is 1 plus radical 2. So if we multiply top and bottom by 1 plus radical 2, there's a little bit of a situation we get into, but it's not too crazy. So we get 2 times 1 plus radical 2, I'll leave it like that, over 1 plus radical 2 times itself. That's really just a binomial squared. So notice that's going to be the sum of the squares, so 1 squared plus radical 2 squared, so it's just 1 and 2, plus in the middle, 2 times our product. The product's radical 2, 2 times that is this. Great. Now what? Now these combine to 3, 2 radical 2, 3 plus 2 radical 2. So that's going to be when you distribute this into that guy, but then distributing it into here cancels those, so we get minus 1. So we get 3 plus radical 2, 3 plus 2 radical 2, really, and then minus 1. So now notice, if we distribute this 2 on top, which probably we could have done before, we get 2 plus 2 radical 2. On the bottom, if you combine this 3 and negative 1, notice 3 minus 1 is just 2, so this is also 2 plus 2 radical 2. So funnily enough, this is actually just 1. Awesome. Alright, so we've done quite a lot in this video. The only thing I haven't really done is shown you the applications of hyperbolic functions, and I'm not going to, but I'll say that they exist and they're kind of abundant. They pop up every now and then. Sometimes the only real one I can think of off the top of my head is in construction, like with bridges. So I guess that would be civil engineering, something like that. I'm sure they come up in electrical, even in electrical engineering. Engineering is where I see maybe the hyperbolic functions coming up more often than any other topic I could think of. But they creep up every now and then. You won't really see them too much in Calculus 1 and Calculus 2 beyond this, but it's good to see them because, again, when you do see them come up, we've at least established some properties, so that's nice. So that's the end of chapter 3, so I'll see you in the next videos for chapter 4, where we'll be taking a look at a lot of applications of derivatives. That's going to be a whole lot of fun, so I'll see you in the videos for that. Hope you enjoyed this. Thanks for watching, and I'll see you then.